So welcome to your own channel, Paper Money. I am Bipul Gupta, and this is lecture number 11.
Good
So
evening,
yes,
sir.
good evening. Yesterday we had covered this quantum operator, angular momentum operator, right? So
Yes, sir.
yeah, so I hope you were able to do the problems which we discussed yesterday.
Yes.
All right, I gave you for homework. All right, so today we'll start with this thing that the Schrodinger equation. So we'll do problems also uh, from previous year. All right, so let's start. So in this thing, you have so the next topic is Schrodinger wave equation. Now, for some of you who have gone through the previous lecture, it might be a revision thing. And for those who have not done it, please take notes. All right. So after this lecture only, I started the lecture series from scratch. So what we have is Schrodinger equation. Schrodinger wave equation. Now, once it was found that the particles show wave behavior, so it was to come up with some model, some theory which which one can use to explain this wave behavior and quantify this wave behavior. So somebody suggested Schrodinger to present this de Broglie hypothesis.
Sir,
Yes.
so will you be solving yesterday's homework question?
Sorry.
Will you be solving yesterday's homework question?
Yesterday's homework question.
Yeah, there's one question I couldn't solve it, sir. Would you?
I asked you in the beginning. So did you join late or something?
Yes, I couldn't.
No. So then I'll start this at the end.
Okay, no problem, sir.
We can do this. Okay. Which question it was? What was the statement of the question?
It was the second last question, sir. It was canonically conjugate momentum operator. That one.
Canonically conjugate momentum operator. Oh, all right. So I'll do it in the end. So what from now onwards, what I'll be doing is, since this videos are also uploaded to YouTube. Okay. So there is another audience who are looking at the lecture. So these kind of interruptions make the things a bit difficult for them to follow. So
Okay,
what we can do is we'll have in 1 hour we'll have first 45 to 50 minutes of lecture and then last 10 15 minutes of discussion. All right. So in that way, everybody benefits, right?
Okay, sir.
Okay,
So
sir.
when you have a question in mind, just keep in mind till the end of the lecture, and then we can discuss. All right. And homework problems also we'll discuss at the end. Actually, I told you that before the class I'll be start doing that, but I then thought about it. So I thought that because people are also watching on YouTube, for them they don't know what the pattern is. All right, how we are doing these lectures. Okay, so it's better if we have all the class material at the beginning and then 10-15 minutes of discussion. Okay, so if somebody is not interested in the discussion, then the person might skip that part. All right. So for a particle of mass m, now what happened was Schrodinger, somebody suggested some famous scientist, I don't remember his name, but he suggested Schrodinger to think of some wave equation. If the behavior of the particle is of that of a wave, then there might be some wave equation which the particle might follow. All right. So then Schrodinger went back to his own university and then worked on this problem, and he was able to come up with what we known as the Schrodinger wave equation. All right. So we'll look at it. How the equation looks like. So if we have for a particle, so we have a particle of mass m moving under the potential. Okay, now whenever I mention potential, this is actually the potential energy. In quantum mechanics, we say that the potential energy is like the potential as the potential. All right. So don't confuse it with the EMT theory. If you have learned that the potential there, okay, that potential is different from this one. This is the potential energy. All right. So the Schrodinger equation, is given by, let's keep S capital. Schrodinger equation is given by, all right, this is H cap psi. Now psi is the wave function which is dependent on position and time, and this is E operator, and we have X t. All right. Now this is the equation which Schrodinger came up with, and even Feynman said that where did it come from? So he said that this was all from Schrodinger's brain. Now, in some books you might find that they take the wave function as to be this kind of function, like psi naught e to power I kx minus omega t, and then they prove RHS is equal to LHS. Now that is not a proof. Okay, that is not what I call it as a proof. Proof, if you want to have a look at the exact proof of this, there is a derivation, but it is much more advanced and very time consuming. So you'll if you when you learn Hamilton Jacobi, there is a approach using Hamilton Jacobi and Klein Garden equation where you can derive get this Schrodinger equation. All right, so that is not required at all at this stage. And the thing is, you can think of it as the way you treat Newton's equation. In Newton's equation, what you have is you know that this m this is double derivative with respect to time. Now this is equal to the force, external force. All right, so this is, you don't try to come up with a proof of this. Okay, you know it's you have been learning for a long time, you know it's true, it works. So that the same way we can take this as also the same, in a similar way we can take it as that this also works. And it's even HC Verma in his book says that my seniors told me that it works, and then I read in many books that it works, so it is taken at as it is. But there is a proof, but we don't require to get into that. But if you are trying to prove it just by taking the wave equation, it is not exactly a proof. All right, proof means if you have something, if you are able to create this equation from some basic principles, okay, that is the derivation. Okay, so but yeah, you can use this wave equation, this wave function, to just put the operators, and you will be able to prove RHS equal to LHS. All right, but that is not a derivation. Now where now I have motivated the fact why we are using this equation as it is. All right, so you have this thing, the Hamiltonian operator is t cap plus Vx. Okay, now this is the Hamiltonian operator, this is called the Hamiltonian operator. All right, now, and then there's the energy operator, the time version, which is given by I h cut. Now this is not a, let's write it as a time derivative. All right, so let's see if we put these things down, what we get when we operate this in the wave function. So what do we get? So minus h square by 2m. Now if I expand this thing, the kinetic energy operator is what? Px square by 2m. Okay, so this is minus h cut square by 2m double derivative with respect to x. All right, so we can use this thing here in the Schrodinger equation. All right, so this is psi xt plus Vx, all right, multiplied by psi xt is equal to I h cut derivative with respect to time. Now I write a partial derivative because now both sides should be written as a partial derivative, because this is both a function of time as well as position. Okay, yeah. So this is the explicit form of the Schrodinger equation. Now this thing we can see that this equation is this expression is a partial derivative, like partial. This is a partial differential equation. This is a partial differential equation, all right, in two variables, in two variables. Okay, so this is xt, all right. Now the thing is, we separate this into two parts. So we have the time dependent part. So we are trying to separate this equation. The way we solve the partial differential equation, we use the separation of variables. So the time dependent part and time independent part. Time independent part. So we have two parts here. All right. So in this case, we are assuming something which is important for this all these calculations, which is that we are assuming that the potential is independent of time. Independent of time. Now this is very important. If this was not there, then it's difficult to separate the way we are going to do this. All right. So let us assume that psi of x, psi which is a function of xt, can be written as a product of two separate functions, one which is only a function of x, the other which is only a function of time. Okay, the capital X and capital T are the functions which we are splitting the wave function into. Now if I put this in the equation, okay, let's say this is the equation which let's label it to be 1. So we put these equations, this value of psi in equation 2. So from equation 2, sorry, from equation 1, what we have is minus h cut square by 2m derivative with respect to x. Now if you put this thing, capital X and capital T, and then we have the time independent potential and multiplied by the wave function which is xt, and finally we have the RHS which is partial derivative with respect to t, and then we have the wave function which is xt. Now if I just operate this, so what will we get? What will we get here? The t will come out, right? So we can write this as the total derivative, because this is only a function of position. Now plus, now this is vxt is equal to I h cut. Now this one also becomes a total derivative with respect to time, because the function which is left out in the derivative part is the time function. All right. Now dividing both sides dividing both sides by xt. All right. So what will we get? We'll get is this equation. So this is minus h cut square by 2m. This is 1 by, now if I divide by this will be 1 by x, derivative with respect to x square, second double derivative with respect to x. This is vx, which is a function of x. Now in this case, what I'm doing is I was dividing, so this will be also be 1 by t dt by this. Now since we have this thing that on this side it is only a function of x. All right, this is only a function of x, only a function of x. All right, and this side it's only a function of, or it's better to write function of time only. Okay, so what if two functions, okay, if two functions are, say this is function of x and this is some function of y, these two functions will only be equal if both are constants. All right, similarly here what we have is both sides are equal to some constant. Now that constant happens, like in the final equation after derivation, it was found that it is the energy. All right, so that is why we represent this using E, which is a constant. Okay, we could have represented it using anything else, but the final form which we get from the equation is that these quantities are equal to the energy. All right, which is a constant. Now the dependent part time dependent part time dependent part uh, let's do it. So time dependent part is the second thing, the which was only a function of time. Okay, so let's take it and then solve it. So this is my I h cut by 1 by t. This is derivative with respect to time, and this is equal to E. All right, now if I solve it further, now this is a differential equation, so let's solve it. So this is minus I h E by h cut. This is with respect the dt. So if we're integrating both sides, now you should, I am doing this derivation because I'll do those derivations where questions are being asked from the which involves the derivation part. Okay, so this is one of them. So integrating both sides, okay, of the above equation, what we get is ln t, which is log natural log t, minus IE by h cut, and then t plus ln c. Okay, now log is introduced in the constant to facilitate a simpler equation. Okay, a clean looking equation. So this is minus et by h cut. Now this will give us, if we rearrange, what we'll get is e to power minus IE by th cut. All right, now this one is what you should remember. All right, now this thing, you can see that this form of the solution of the, now this one is the that part of the wave function which is only dependent on time. Now you can see that this is independent of v as well. There is no mention of v, independent of potential Vx. That means that whatever the potential is given to you, be it one-dimensional potential well, or this thing infinite squirrel potential, or then you have harmonic oscillator potential. In every case, you'll have this form only. Okay, for the time-dependent part solution, you don't need to change it. Just that you have to take care of this energy. Everything else is it can be taken as it is. Okay, now these constants will change accordingly. Okay, but the one only thing you have to add is this energy part. All right, so you don't need to solve this part every time. Okay, now next let's see. So this is you should remember the solution to this. It should be remembered by you. All right, now next one is the independent part. So let me write down, this is time independent part. All right, so this one is minus, now we are taking the x only, the function of x only part, which is this part. All right, plus this is bx is equal to e. Now if we rearrange, all right, we like to rearrange things and so that it looks neat and clean. So let's do that for this. So if we write like this, okay, so we bring everything to the left hand side. So we are left with this equation. Okay, and now we cannot do anything further because we, although this first term and the second term is a constant. First term is at the differential part, and then we have this thing which is a variable which depends on x. So unless we know the form of the vx, we cannot go further, like we cannot solve this equation further. So it depends on the solution of this thing. Now you don't need to remember this. Okay, this you can get it from whenever you have a Schrodinger equation. Just you have to rearrange this part. Okay, or you can directly write down like this, that this side you know that uh, this is the form of the equation. All right, you can remember this part, so it's better if you remember this part. All right, now so you don't waste time in deriving this. All right, the form. So the solution of this equation, all right, depends on the nature of Vx. All right, now let's say, since psi, now this is done, that okay, we cannot solve further without knowing the nature of, without knowing the form of the Vx, we cannot solve this further. That is done. Now if I try to conclude this thing, whatever calculations we did, that we have split this wave function to solve this partial differential equation. We have split this into two as a product of two functions. So one was the function of position, one other was the function of time. Now we do not know the form of the position, this part, so we are left with this thing, that we can write this. All right, so for a given wave function, we can which is a function of time, the total wave function can be represented in this format, in any type of potentials which is independent of time. All right, so in general what we can do is, in general, okay, if we have the we if we consider, if we consider if we consider the I if we consider superposition of states, superposition of states, all right, so in that case we have, say, this function which is summation of, like, from, let's take the change the variable to be k here, okay, instead of I. Now this is also function, this is a function of x, and then we have e k t by h cut. All right, so this, if we want to expand it, so this would look like c1 x1 e to power minus I iota e1 t by h cut plus c2 x2 e to power minus iota e2 t by h cut plus, then we have this, let's take it to be one of the terms, so ek t by h cut. All right, so this is the form. All right, now this is what we get. So what we have to do is, we have to just find out the energy corresponding to this state, this energy corresponding to this state. Okay, and then we can write like this. Okay, now in this case, the ek is the energy, eigenvalue, of the kth state. All right, so we'll use this when we have superpositions of states, whenever we do some potential. All right, there we'll be applying this part whenever we have been asked the total, about the total wave function, okay, or the time evolution, so to say, the time evolution of a wave function. So in that case we have to add this factor. All right, so how do you do it? We'll do it for each potentials. Now let's talk about free particle. Now a simple application of this Schrodinger equation, which is a free particle. All right, now free particle is something which does not feel any force when it's moving in the space. Okay, so when there is no force, there is no potential. Okay, so a particle on which no external no external forces are acting, no external forces are acting, and this, say the examples are electrostatic, electrostatic force, gravitational force, all right, and then we have, say, nuclear force. So these are the forces. Now is called, if no forces are like acting on the particle, then this is called a free particle. Okay, so if there is no there are no forces acting on it, then in that case you have this thing that psi is, say, this is equal to psi x. Now we are not solving this thing because we know that what the solution of the time part is. Okay, we are writing the function, the psi as a function of x. Okay, now vx is equal to 0, and since we already said this what a free particle means, which is there are no forces. If no forces, if no forces are acting, if no forces are acting, we have pe, the potential energy, is equal to 0. All right, so in this case we're solving only the time independent part. Okay, that's why we wrote it, the wave function, as a function of x only. All right, so e psi. Now if you solve it further, what you get is this is minus 2me by h cut square psi. All right, now in this case, if you can rearrange this thing as this is equal to minus k square psi, where k is defined as 2me by h cut square, where k is the wave number of the de Broglie wave associated with the particle. Okay, so this is real positive quantity. This is defined as a real positive quantity. All right, now let's talk about the solution. Let's talk about the solution. Now the solution. So we know what the solution is. Like the function can be written as a psi a e to power ikx, or it could be written as b e to power minus ikx. All right. So any of these equations will satisfy this equation. These solutions will satisfy this equation. So if we want now, what does it? So what does, how do we interpret this thing? So what we can do is, let's talk about the momentum of the free particle. Okay. So if I apply this thing, so this is e to power ikx. Okay, when we apply this, you get h cut k e to power ikx. All right. Now you can see that this thing, this is the eigenvalue equation, and this is the lambda. This is the eigenvalue of the momentum operator in this state. All right. So this is the eigenvalue what we got. If I try to measure the momentum for this wave function, we'll get this as an eigenvalue. Now we know this from that we did earlier discussion, that E is equal to h cross omega and P is equal to h cross k. All right. This represents, so we have this thing that e to power ikx represents the part represents particle or move represents a free particle. Okay, free particle moving along positive x direction. All right, it is moving along positive x direction. Now similarly, if we apply px on minus ikx, all right, what we'll get? We get minus I h cut k or minus I kx. All right. So in this case, the eigenvalue here is the lambda is minus I h cut, sorry, minus h cut k. Now in this case, we can conclude that see the momentum. This is the momentum. Now in this, the momentum is, it's a vector quantity. So the sign has changed. Okay, sign has changed. That says that the particle which this wave function represents a particle which is moving in the negative x direction. So we can write like this, that this represents a particle, moving, a free particle, of course. Okay, a free particle which is not feeling any force, moving along negative x direction. Okay, all right. So k can, in this case, we do not have any restriction to k. All right, so k can, the conclusions are here. Now k can take any value. It's not quantized, as we'll see in other potentials. K can take any value because it depends on now k only depends on the mass and the energy of the particle. Okay, so energy, if you increase the energy of the particle, then the k will change, and you can continuously vary this energy here. Okay, now k is not quantized, that means the energy is also not quantized here. Therefore e can take any value. Okay, uh, the energy of the particle is continuous. Energy of the particle is continuous. All right, now the thing is, if in this case this is not exactly the wave equation for a particle moving in this, because the particle is a quantized, it's the energy is localized. Okay, the particle is a localized thing. Wave is infinite in extent. Okay, so what we do is we take a superposition of lot of waves, or we simply take a Fourier transform. Okay, and we try to make a wave packet out of it. Okay, we try to make a wave packet, and then we study it, but I won't get into that discussion. All right, so this is what you require for your exam point of view, and let's solve from some problems. Let's see, let's take a TFR problem. uh, Wait a minute. So okay, so this is the question given. TFR, all right, yeah. So the question is, a particle is moving in one dimension, is moving in one dimension all right, under a potential Vx such that for large positive values, of x, okay, we have Vx is like like of the order of x is approximately equal to k into x to power beta, where k is greater than 0 and beta is greater than equal to 1, if the wave function is if the wave function in this region has the form all right, psi x, which is of proportional to, like, of this exponential function, which is x minus lambda. Now the question is, Which of the following is true? Which of the following statements, which of the following is true? Okay, so this is let me write on the options. This is lambda is equal to beta by 2 plus 1. B is equal to, B option is lambda is equal to beta. C option is lambda is equal to 2 beta minus 2. And D option is lambda is equal to beta square by 2. Now this is a TFR question, TFR 2015. Okay, so TFR asks this type of questions which might not directly make any sense. Now the first thing what the student does is, if the student knows about the linear harmonic oscillator, then he tries to come up with this thing that, okay, let's take beta to be 2. So this will have this format, the waveform of the wave function should have the form of a linear harmonic oscillator. All right, but this might not be true in this case. Okay, so just go through the question once and then think about it. All right, and I'll give you let's say 1 minute is enough to see the question. All right, another 1 minute to think about it. A particle is moving in one dimension under a potential Vx such that for large positive values of x, for large positive means away from, very far away from the origin, Vx is given by this format, right? Where k is a positive quantity and beta is greater than 1, means it's like uh, a potential which is in the upper half of the uh, coordinate system, like the coordinate system, right? So if the wave function in this region has this form, okay, the form is given, the wave function of the particle which is in this wave potential, which of the following is true? So I've already given you a hint how to solve it. Did you see the hint? I'm discussing this just after your this thing, the derivation of Schrodinger equation. So you just have to apply Schrodinger equation. All right, apply the Schrodinger equation. You have the Schrodinger equation. Put these things in that equation, the psi
Okay,
and
sir.
dx, and see what you get. So let's take it to be like this. So we have the solution. So let's take that psi x is some constant, say a times exp, and this is mine x to 1. All right, and vx is already given to be k x. Now this is beta, I guess, right? Yeah. So we have been given this. So we have already given you a hint because I'm just doing it after the Schrodinger equation. So obviously that Schrodinger equation is used here. So you just put this in Schrodinger equation. What do you get? So you have the Schrodinger equation. Now Schrodinger equation, just remember this thing that x psi, this is equal to e psi. Now this is the time. You don't need to remember the time dependent part. You can just directly use this thing that this is minus h cut. This this will give you, all right, plus, okay. Now, so what do you get here? Plus Vx, okay, Vx psi x, and which is equal to some constant E. So we are just using the time uh, time independent part. All right. So just plug the equations. This is also psi, right? So when you apply this thing, so what do you get? So if you place, are you guys solving it?
Yes, sir.
Yes, sir.
So you just place this equations here. So this is plus Vx, this is k x beta, or this is a e to power minus x lambda, or this is e Now this side is a e to power minus x lambda. All right. So just we have to solve this part. So this is, if you take the derivative, you take the first derivative. So what do you get? So let's remove a from all sides. So let's get rid of a because it's a constant quantity. Let's get rid of it. So what we are left with here is now this will be, if you take the derivative once, so this will be minus lambda x lambda minus 1 e to power minus x lambda. All right, plus now this is k x beta e to power minus x lambda is equal to e to power minus x lambda. All right. Now it's sometimes these kind of questions doesn't make sense in the beginning, but if you apply this first principle that okay, you have to get it out of Schrodinger equation, just keep solving, you'll get some idea what to do. Okay, now further you take this derivative again. All right, so what do you get now? Let's get rid of lambda here and minus sign here, so plus lambda, this becomes plus lambda, and then we have this thing that lambda minus 1, and then what do we have here? This is lambda minus 1 and then x lambda minus 2, and this is as it is. All right, and then we have minus lambda x lambda minus 1, and then again we have minus lambda x lambda minus 1, and this is x lambda x to e to power minus x lambda. All right, plus k x beta. Right, now this is e to power x lambda and e minus x to power lambda. I hope everybody is getting this result. So if you take this term out, the e to power minus x lambda term out from everywhere, so you're left with is inside this you have lambda minus 1 x lambda minus 2. All right, minus, now this is the plus sign, so
Hello.
we'll have, yes, tell me.
I think there is an extra lambda in the second term
Extra lambda in the second term. Okay, I did
because
take,
lambda.
I took lambda outside, no?
Yeah.
Yeah, all right, thank you so much. Okay, yeah, I took the lambda outside, so I forgot that. So this is fine, right? So if you have this thing that you have lambda, now this is lambda minus 1, this is twice. Now we have gotten rid of this e to power exponential terms, and then plus this will be kx beta is equal to e. All right, now in this case when it says that, it says we are talking about the large values of x. Okay, so for large values of x, let's see which term will survive. Okay, for large values of x, now this term is bigger than this term. Okay, for large values of x, for large values of x, this term x to the power lambda minus 2, this one is less than this term. All right, so we can ignore that term. What we are left with is, okay, this is it's larger than this term. Now we can get rid of that term, so we have lambda square h square by 2m, and we are left with x 2 lambda minus 1, and then we have plus k x beta is equal to e. All right, now the thing is, this is a very important step here. Okay, now this is what we in most of the problems, this is the most important step, that how do we simplify it further. Okay, now we know that this quantity is a constant. All right, this quantity is a constant, e is constant, right? We did it in the Schrodinger equation in the beginning. E is a constant. All right, now if this has to be a constant, this side also has to be a constant. Now this side has to be independent of x. Now when can we make it independent of x? Okay, either this, that all these terms are 0, but then if these terms are these constants are not 0. Okay, these constants are not 0, so we cannot do that. right? So what are we left with? If we make the powers of these two x's equal, if we make the powers of these two x's equal, all right, so in that case, let's say that this is equal to beta, all right. So now we can write like this, that this is lambda is equal to beta by 2 plus 1, all right. Now if this happens, what we can do is we can write like this, we can use this, instead of lambda we can put this beta and see what happens. So this is by 2m plus so this term becomes x. Now if you put this this lambda, instead of lambda you put this beta by 2 plus 1 minus 1, all right. So this is, of course, both will be equal, so we could have directly written down that this is x to the power beta. Okay, that is what we will get because we have taken both the terms, both the powers to be equal. Okay, so that is what we are getting here. It will be beta plus k x beta, all right. So k x beta is equal to e. Now what we can do is we can see we have already gotten our answer. Okay, but I wanted to show you what is happening here. If you take the x beta common, so lambda h cut square by 2m plus k is equal to e. So in this case, to make this term, to make this quantity a constant, what we can simply do is we can put this thing equal to 0. All right, we can put this thing equal to 0, and that can be made because k, all right, in this case it can happen because lambda is not given anything. Lambda, there is no mention of lambda here. What is required is k has to be k is positive. All right, so we can choose a lambda in such a way that we will get this to be 0, and if we get this term to be 0, we can get rid of we can make the whole thing, this whole thing, as constant. All right, so that solves our problem. So the answer to this question is this one, that lambda is equal to beta by 2 plus 1. Now this is very difficult for somebody to click during the exam, like if you don't know how to tackle these kind of problems. But what I suggest you that if this kind of problems come up, you just start using the basic principles, and along the way you can figure out what to do. All right, and take note of whatever the assumptions has been made in the question. All right, so this is the which option is it? This is A option.
Sir, can you please repeat the last thing, that how we make it constant?
See, what we are doing is this thing is clear, right? Why did we get rid of one of the terms? Because
Yes,
see,
sir. Yes.
for large values of x, this will be this power will be higher than this power, right? This is
Yes,
because
that-
twice of that. All right, so that is done. Now we have this format, which is for large values of x. This is the dependency which we have. Now what we want is we want to make e is a constant, because in the Schrodinger equation e is the constant. Okay, so we want that this side also should be constant. To make this constant, either these terms become 0, but this is not given to be non-zero, k is greater than 0, and these terms are non-zero. All right, so we cannot make this to be 0 by putting these constants to be 0. All right, so what we need to get rid of is we need to get rid of we somehow have to make this term equal. This power and this power, if both are equal, say we have some term which is ax square, and we have bx, say some term k, and we want that this should be equal to 2. All right, so we know that if we put ax square plus bx, now k equal to 2, if we put k equal to 2, in that way what we can write is we can write like this. All right, okay, and then we can arrange this thing. We can make sure now this is I think this example went wrong somewhere. Let's take it to be 0. All right, now 0 is also constant. All right, so we can adjust a and b such that this term becomes 0. All right, so this is an example which I gave you. Now in this, yes, tell me.
Sir, in this equation, like we need e to be the constant, so we need the expression to be independent of x.
Yes.
So can't we say like this, that 2 lambda minus 1 equal to beta equal to 0?
2
Because
lambda
2 lambda minus 1 bracket
till
minus
lambda
1
minus 1
equal to beta equal to 0.
0. No, beta is not 0, right?
Okay.
Beta is not 0. All right. So we
Not
want
by
to
0.
beta is, it's given in the question. It's if it's 0, then the question, it's nothing to start. Then everything becomes 0. Okay. The potential becomes constant then. All right. So what we want is this this term to be constant. Now we can make it constant. There's only one possible way. Okay, that we take this to be this if we take this these two powers to be equal, and somehow we can take this common, and we can of course make this to be 0 and make it independent of x, and this is also a constant, right? This is also a constant. This is also a constant thing. If we try to make this 0 and 0 is also constant, this also becomes 0. Okay, so we have an option to make this term satisfy this whole equation. All right.
Sir, this is what I was asking, sir. If we make the 0, then E is constant, but only a particular constant, that is 0.
Yes.
Are we allowed to do that?
Yeah, it could be done, no? So what is the issue there? So it could be any constant, and 0 is also a constant.
Okay, sir.
All right. So if you say that, okay, if you say you don't want it to be 0, then how do you get rid of x to the power beta?
There seems no way.
Yeah, so that is only the way which where we can get rid of this thing. So this is the only way. So sometimes these kind of questions come up. Okay, so what happens is generally in JEST and TIFR, mostly in TIFR, the questions are set from maybe a professor is doing some research work. Okay, some research work he's doing, and he finds some interesting approximation questions like these. Okay, and then he modifies it accordingly for your level and then puts it in the exam. Okay, so these kind of so this is associated with some kind of research problem. All right, so there sometimes what happens is they might not give so much thought into it just because we can approximate this. So this is just an approximation. All right, so this is this holds, like if you can prove it for one, like if 0 is the answer, then fine. Let's say that, okay, the energy of the particle is 0, no problem. All right. Now, one thing is that the energy of the particle cannot be 0 because if this is a bound state, okay, if this is a bound state, then there has to be a minimum energy. All right. So yeah, I get your point that there is some there's some conclusion issues with this, but this is how you can proceed with this problem. All right, there is no other way I can think of. All right.
Okay, sir.
Because see, if this is the you have been given this potential in this case, and if it's a bound state, then the minimum energy cannot be 0. All right, it has to have some minimum energy. So, and for this we are getting energy equal to 0. Okay, let me think further if there's some other solution, but I've thought about it a lot of times, so this is what I always conclude. All right. So this is the answer. Okay, so you just have to compare the powers and see how you can reduce this equation into a constant value equation, constant thing. And let's do another problem. So I'll give you this as a homework. Okay, then we'll proceed further. What is the time? Okay, it's already, so this question took a lot of time. So there's a question from JEST. So the ground state. So I'll discuss yesterday's question also. Okay, just let me give you this question. So apart from normalization, of a particle of unit mass moving in a one-dimensional potential, moving in a one-dimensional potential all right. Now this is Vx is Vx. Now the wave function is given, the ground state is given to you as this. Now ground state is the lowest energy state. Okay, you don't need to worry about it. This is cos hyperbolic root 2x, and the potential is Vx, all right, in suitable units, so that h cut equal to 1 is up to, now h cut they have taken it to be 1, okay, so up to an additive constant, all right. So this is a question. Options are, now this equation has two methods to solve it. One is the usual method, the Schrodinger's way. Okay, so I'm giving you the hint also how to proceed, and the other is plotting. If you can plot the functions, you can easily solve this question. But if you are not good with plotting, or if you have not watched my videos on plotting on YouTube, then you might have some problem. This is cot hyperbolic root 2x. All right. So I'll give you the answer if you want, because see, I'm giving you the answer, then it spoils everything. But still, I'll give you the answer if you want to check. This is the answer. Okay. So this is the homework problem for you. And yesterday's homework problem was, so did you copy this down? Okay, you can
Yes,
get
sir.
it from the notes. Okay, if you have not copied it, you have you must have you'll get the notes. So this is from just, this is also an old problem, but it's a very good problem. Okay, so if you try to solve it using Schrodinger equation, it will be lengthy, and if you try to solve it using graph, it will be easy. Now graph, I have not discussed it much, how to plot the wave functions given a potential, but let's see how many of you can do it. So the question which was asked yesterday, I think the CSIR problem, right? 2000, which one was it? This one, so December 2017.
It is option B.
Yes, sir. Yes, sir.
I got this option B.
Yeah, so it's not that difficult. Okay, so okay, not a problem. If you're not able to do it, don't worry, but try to see and observe and figure out how we solve it, how we approach a problem. Okay, so we have this question from previous homework. Right, so let me highlight this thing. So this is the question. All right, so this is given to you. Now you have to just solve the commutator operator. Okay, so it's given to you that two position of momentum and position operator are given. The commutator is given as this, and if it says that is 0, this commutator is 0 if, so you have to simplify this thing. Okay, nothing much to do, just follow the, this is all mathematics, nothing, there's no physics out here. So this is 1 by 2m p square plus beta x square 1 by m p square plus gamma x square, all right, equal to 0, right? This is what is given to you. Now you have to find out the relation between beta and gamma. All right. So just take these things common. Now this thing can be taken out. Or you can just write it like this. Just apply the linearity property. Okay. So this is the first term. Then you have beta x square 1 by m p square. Okay. Then you have plus. You can write like this, that this is so the two terms have been done. So this is 1 by 2m p square gamma x square, and then we have plus, this is beta x square, and then you have gamma x square. All right, so this is equal to 0. Now just see this will be what? This will be 0. Both are p square. All right, this is 0, and in this case both are x square. This is 0. So what are you left with? These two terms. So in this case, what happens is you can take out the constants as it is. Okay, so b by m, this comes out. So you have x square px square plus, now in this case you have 1 by 2m. This becomes, this is p square. Now this is x square is equal to 0. All right. Now in this case you can rearrange this thing using the anti-symmetry property. So if you use the anti-symmetry property, in this case, in both the commutators, what
Sir,
will
there
you
is
get?
gamma also in the
Sorry?
second term. 1 by 2m, so there is gamma also in the second term.
Second term, this one.
No, sir. So the
Okay,
second.
in this one. Okay, there's a gamma here. All right, there's a gamma here. Yeah, you're right. There's a gamma here. Now, if I rearrange this now, and let's get rid of the m. So what we are left with is, you can write like this: x square p square. Now this is minus, this is gamma by 2. Now this can be written as x square p square. All right. Now from our experience, we have already done this, solved this problem, that this is not equal to 0. X square p square is not equal to 0. All right. So if we take this common, gamma by 2, and this is x square p square is equal to 0. If this is not 0, this is not equal to 0. Okay, this is not equal to 0. That means what should be 0? This should be 0. So beta is equal to gamma by 2. All right, let's see which option is this. So gamma is given to be 2 beta. Gamma is 2 beta. All right, so gamma is 2 beta.
Sir, in this question, what is the phrase canonically conjugate momentum operator
It's
mean?
called, when you do in classical mechanics, we call this canonically conjugate. All right. Now we have to define things there. Okay, this is just a name given to it. All right. So just don't worry about it. That x and px are they are called a canonically conjugate. All right. So this is a classical mechanics term when you do this Lagrangian Hamiltonian. All right. So I'm not getting into that right now. So don't worry about it. Whenever you have been given an operator, it's a quantum mechanical question. Okay. If the operator was missing, then I would have treated this as a classical mechanics question. Okay. All right. So let's sign off for today. Any doubts? Anything? Any query? All right then. Take care.
Thank you, sir.
All right.
Thank you, sir.
Okay. So if you now, this is an announcement for the YouTube who are watching it online. So please make sure that you like and subscribe, and so that, see, if something is good, if something is valuable for you, it might be valuable for everyone and somebody else also. And I understand that you when you get hold of something very good, and then you don't want to share it with your friends. Okay, but the more you share, the more you gain knowledge. You can discuss with friends, you can talk to them. Okay, so you learn more, and in the process also, I also learn from you. Okay, so I'm not the guys who are attending the Zoom lectures, I'm not telling them to do, they are already subscribed to my channel, but the others who are looking at it, I don't like marketing or selling things like this. Okay, but the more you, because some of you were not able to find out these lectures after they knew me personally, then only they came up, found these lectures. All right. So I want that this, if you subscribe and comment and like, this will come up more on the search results. All right. So thank you for watching. Have a great day.